think, wow, this is kind of neat. You're only using inorganic caustic. I'll tell you in a minute why that's kind of neat. Okay, the enzyme is here, glycogen synthase. And the enzyme here is, oh yeah, glycogen phosphorylase. So if you were the hormone glucagon and the liver released you in response to low blood sugar levels, what kind of activity, how do you want to change glycogen synthase? You want it to work faster or slower? Glycogen synthase. Yeah, you want to slow it down or stop it altogether. Okay. What would you want to do with glycogen phosphorylase? The glycogen phosphorylase also. Want to slow it down or speed it up? Yeah, speed it up. What if you were insulin? What do you want to do with glycogen synthase? Yeah, you want to activate it because this is a great way to get rid of blood sugar. Get it picked up by the liver, and the liver can store as much as it can in the form of glycogen. You don't want to be breaking down glycogen when the blood sugar levels are already high. Okay? So let's think about epinephrine for a second. Okay? What effect does epinephrine have on blood sugar levels? It's a flight or fight response. It's going to increase. Does it care what the current blood sugar levels are? No. So epinephrine is going to be released to raise blood sugar levels so you have enough energy to either run away from the danger or fight the danger. So perfect response. Okay, so epinephrine is going to mimic glucagon. The only difference is glucagon is acting in response to low blood sugar. Epinephrine couldn't care less what the blood sugar is responding to the activation of the flight or fight response. Okay, so the epinephrine binds to a different G protein coupled receptor that's going to do exactly the same thing as glucagon. Okay, so sometimes you see the same response, but the trigger, the hormone, is going to be different. This is for people who like endurance metabolism. I don't know if this is going to be on the video. Glucose 1 phosphate. And the glucose 6. Okay, and this goes down through glycolysis, Krebs cycle. Okay, all the way down to, so you break all this stuff down to ATP, carbon dioxide, water, okay? Glycolysis, right? You run the glucose 6-phosphate through glycolysis, run the carbons through the Krebs cycle, and you get a whole bunch of ATP. So if you needed to preserve energy for as long as you possibly can, would you rather use blood sugar as your energy source or glycogen? In order to get that glucose into glycolysis, into the glycolytic pathway, if you're using plain old blood sugar, you're going to have to split an ATP. Okay? If you're going to use glucose to get glucose into the glycolytic pathway in Krebs, you're going to spend, it's not going to cost you an ATP. Okay? You're going to use inorganic phosphate to phosphorylate that glucose. So it's a subtle energy saving step that I think in the long run. And besides, you only have about 5 minutes worth of blood sugar anyway. Okay, so let's look at what happens once we've activated the glucagon G protein coupled receptor. And I'm going to rewrite some of this on the board. I'm going to squish it. Floating off. Okay, so we just kind of went from this stage to this stage where we separated the beta gamma, sorry, that's unreadable. Okay, we have the alpha subunit, which is, sorry, this should be GDP. Now we're going to, I want to take a little look at adenylyl cyclase. Adenylyl cyclase, the structure of it looks a whole lot like the cystic fibrosis protein. So I'm going to do a little mock-up here. And let's see, inside the cell, the enzyme is on the inside of the cell. 6, and then there's a great big, huge, complicated domain. There. 1, 2, 3, 4, 5, 6. And another complicated domain. And we look at this. Look at exactly how the cystic fibrosis protein is organized. It's like there's 2 halves of the protein. And I don't know if there's any evolutionary similarity between the 2 proteins, but they are structured very much alike. Okay, so there's ATP. And both of these are, in cystic fibrosis protein, both of these messy domains on the cytoplasmic side are ATP binding cassettes. That's where the ATP is hydrolyzed. I'm guessing that's also true for cyclic AMP, that the ATP is hydrolyzed in one of those domains or both of those domains. And here is cyclic AMP. I can never get this wrong without cheating. I know it doesn't really look like that. Okay, so there's the cyclic part, where the phosphate group is actually attached to the 5' carbon and the 3' carbon to create this, that cyclical shape. This is actually fairly short-lived. Okay, it's going to be broken down fairly fast by cyclic AMP phosphodiesterase. Okay, and this is adenylyl cyclase. Okay, and the product of cyclic AMP phosphodiesterase is AMP, just that cyclical component of cyclic AMP broken down. So the amount of cyclic AMP in the cell depends on which of these two competing enzymes is more active. If adenylyl cyclase is more active, you see a buildup of cyclic AMP. If cyclic AMP phosphodiesterase is more active, you see low concentrations of cyclic AMP. Okay, so it's just kind of like phosphorylated proteins. The amount of phosphorylated proteins depends on protein kinase activity and phosphatase activity. Here's another one that's really dependent on which of these two enzymes is more active. So when glucagon is present and has it activated the G protein coupled receptor on liver cells, which enzyme is more active? Adenylyl cyclase or cyclic AMP phosphodiesterase? We are going to see the buildup of cyclic AMP, right? So we're going to have to activate, so adenylyl cyclase is much more active than cyclic AMP phosphodiesterase. So we see the accumulation of cyclic AMP. It's not being broken down fast enough by cyclic AMP phosphodiesterase. Okay, oh good, we have a little bit of time to look at. So what does cyclic AMP do? Okay, that's our second messenger. Okay, so far all we've done is created a second messenger, and so far we've done this all at the cell surface. So all of these proteins are cell surface proteins. Okay, but now we got to go internal. Now we have to get the message to farther down into the cytoplasm where the glucagon is being stored and where you're going to find the enzyme glycogen synthase and glycogen phosphorylase. Okay, but cyclic AMP is a nice small diffusible compound. Okay, so I'm going to erase all of this, and we're now going to be inside the cell. Okay, any questions so far before we get off the cell surface? You got it?
So,
Yeah, Suleiman, we'll get you right. Yeah.
So does the alpha subunit, the alpha subunit of the protein, does it move across the membrane?
Yeah, it
moves?
It can move. It's going to move out of the way because there might be another alpha sub S that can contact the G protein coupled receptor for activation. So yeah, there's got to be some diffusion. Yeah.
Where did that whole process, so did you say on the cell, so that process that you just drew out there, where is that?
That's happening here with the globular domains of the adenylyl cyclase.
Do they both have both of those steps or one of them?
Well, I don't know about adenylyl cyclase, but I know that the cystic fibrosis protein, both of those blobby parts are have ATPase activity. So it's possible that both of the complicated domains have ATPase activity, in other words, make cyclic AMP. Okay, so that's what's going on here. So this is ATP being made into cyclic AMP. Okay, so this is all at the plasma membrane. Okay, I'm ready to go in kind of dive down into the cytoplasm. Okay. So now we're in the cell. And this is now cyclic AMP. So cyclic AMP has actually a couple of target proteins that it can bind to activate. One is, I might mention it only because there's, I might mention it. Because there's enough people in molecular genetics to make it worthwhile. Okay, so, but the important target, you can drop this. Okay, so you kind of have to make a complex of 4 proteins. And this protein is complex, it's called pKa. We don't, so the complex is pKa, which stands for cyclic AMP dependent protein kinase. Okay, you're probably wondering, why did they call it PKC? That would make more sense. The PKC is already, the name was already taken. Okay, so the catalytic units, the actual cyclic AMP, or the protein kinase activity is in the 2 subunits that are usually called C. And these are regulatory subunits. Okay, they have no enzymatic activity at all, but they control the activity of the catalytic subunits. And what do you suppose these DENTs are? I bet they're cyclic AMP binding sites. Okay? So when there's a lot of cyclic AMP, I mean a lot of cyclic AMP binds to the regulatory subunits, because they have cyclic AMP binding sites, and that causes the release of the 2 catalytic subunits. Now they're free to float around and phosphorylate a bunch of proteins. What do you suppose is going to happen when the amount of cyclic AMP decreases because there's more cyclic AMP phosphodiesterase activity? The reaction just goes in reverse, okay? So the equilibrium shifts, and the reaction simply goes into reverse. And cyclic pKa is a serine-threonine protein kinase. I don't think I've ever seen it phosphorylate any tyrosine. These catalytic subunits. And the protein gets phosphorylated, but again, a phosphoprotein phosphatase will quickly remove if it's around the phosphate. don't, because the story that we move into next is gonna look like this, and there's no sense in starting it out if we can't finish it. Okay? So that means tomorrow we'll take a look at what are the substrates for PKA. I haven't named them yet, but we're going to see a variety of substrates for PKA and how they impact glycogen, the breakdown or not breakdown of glycogen.